Hello, everybody. My name is Hamed Alidiat Montero, and I am a PhD student at the Department of Geoscience and Engineering at Delft University of Technology in the Netherlands. My coworkers and I are working on the implementation of data assimilation techniques for estimating earthquake occurrences. We are mostly interested into better understanding the fall slip process occurring in the earthquake source and providing probabilistic estimates of the evolution of the state of stress, velocity, and strength of the faults, which is largely unknown and inaccessible. Here, I will be presenting to you some of the results I have obtained by using synthetic experiments for this purpose, with the collaboration of my colleagues Meng Li and Dr. Ilona van Dinter from Utrecht University and Dr. Frenke Vossenpol from Delft University of Technology. Our motivation for studying this approach is to help addressing one of the major difficulties when trying to provide a forecast of an earthquake event, which is the large uncertainty that exists with regards to the current states of the stress and strength of the faults that produce them. We propose the use of data assimilation techniques, which are most commonly used in oceanography and weather forecasting, to combine the information of realistic numerical models, which represents our knowledge of the physics of the problem, and observations like laboratory measurements under controlled conditions or field observations. There are several data assimilation methods that can be used for combining the different sources of information. In this study, I explore the use of the Ensemble common filter that can be regarded as a Monte Carlo implementation of the least square solution of the Bayesian update problem. Hereby, I show the equation of the Ensemble common filter. In the left-hand side of the equation, we have the posterior of the group of variables that we want to best estimate. These we can call are a part of the so-called state vector that we will call as x. In the right-hand side, we also have the state vector, but containing only the estimation coming from the numerical model. That will be our prior. And to this prior, we're going to add an innovation coming from the information provided from our measurements. That is weighted by the Kalman gain. That considers the uncertainty of our numerical model and the error of our instruments to produce the final best estimation. For our synthetic experiments, we consider the setup shown in this figure, where we represent a straight fault as the contact surface between two sandstone specimens, an upper one and a lower one. We model only a 1D slice of the lower specimen, where we impose in the uppermost node of our 1D model a seismogenic zone by using a rate and state friction law as our boundary condition. And in the base of our model, we impose our loading rate. We consider as our hidden states or unobservable variables the shear stress, the slip velocity, and also the state theta on the fault. And then we extract as synthetic observations values of velocity and of shear stress at a given depth away from the fault. We consider that the medium surrounding the fault is homogeneous and elastic, and we model it using Navier-Stokes equations. Besides, in the seismogenic zone, we use an aging law for modeling the evolution of the state theta with respect to time. Finally, here you will find the parameters and material properties that I use for producing my results. Now, we produce our ensemble by imposing different shear stress, initial shear stress, in the seismogenic zone. In these results that I will show in the following figures, they correspond to having 50 different members conforming my ensemble. First, we will look at the results of the estimation of the shear stress and the velocity in those locations where I have both sources of information, where I have my observations coming from my sensors, and also where I have their information coming from my numerical model. Here, I will show you the different cycles that are represented first in the variable of the shear stress. The black line represents the truth that I am pursuing to best estimate via my filter. Here in the shear stress, we will have an interseismic phase where we're loading the system, and then where it releases the energy, it's called the coseismic, and it represents to the earthquakes. The red dots with error bars is representing the observations from my sensors. And finally, in green, we have the spreading of our estimate represented by these hatchet areas that are between the percentile 16 and the percentile 84 of my distribution of my ensemble. And this solid green line represents the ensemble mean of my filter. This brown line represents the starting time where I am assimilating these observations. And as you can see here, before that time, I have a huge spreading of my ensemble, and it cannot resolve the different recurrence interval and the earthquakes. But after I start with the data simulation, we can start resolving those sharp falls and also the recurrence intervals of my sequence of events. We can see also a nice behavior or good estimates in the velocity. And this is remarkable for such a sharp fall as we have in the fast sleep events that are difficult to take some estimates like the mean. So this is very remarkable for these results of these fast sleep events. Then we can look at the results of these unobservable states that we mentioned before in the seismogenic zone. So we can give a look to what is happening in the estimation of the shear stress at the fault, the sleep velocity, and also the state theta. In these results, I want to compare what will happen if we don't care at all and we only take into consideration the prior information coming from our numerical model, and contrast it when to the case where we are actually looking at the observations from our medium and we produce the estimation with ensemble common filter represented by green. The solid blue line is the mean of only using the numerical models, and we again have the percentile 16 and 84, and the greens of using the data simulation. And what we see is that looking at the green results, we can actually resolve and have a very good estimate of the shear stress also at the fault where we don't have any observations, and that the numerical models by themselves, they don't have any improvement in their estimation. This is seen also in the velocities, and is also observed in the contact edge or state theta of the fall. So after this, we would like to understand or to see how is the evolution of the variables in the different parts of the seismic cycle. What we have here are phase diagrams helping us to understand that. The interseismic phase is represented by blue, and the coseismic phase, when we are releasing the earthquakes, is represented by purple. The arrows are showing the sense of this diagram. What we see is that we have in the coseismic phase, where we have the sharp fall and we're liberating the energy, a good resolution after using our simulation, which is very nice because it's the most challenging part of our estimation. So finally, to sum up, we have tested the performance of our Ensemble Common Filtering framework using a perfect model test. We have shown that our initial results suggest that the Ensemble data assimilation methods provide a useful technique for estimating these earthquake occurrences, and that the state of the shear stress and velocity at the fault are well estimated. And the results also indicate a good performance of the estimation of the variables, even with the difficulties associated with not having a slowly accelerated medium, but fast sleep events, as I mentioned before. Thank you for your attention.